Okay, let me see. I think everyone can share the screen now. Very well. So today is the last talk of the semester, and basically we already had Vadim, I think, speaking about the top spectrum and the Tom spectra and the Pontryagin Tom theorem and today we will see how to calculate the homotopy groups of the simplest Tom spectrum with the spectrum MO and well, another goal. I don't know whether or not we'll get there. Normally, cobordism spectra are quite complicated, but for some reason, MO is well relatively simple as far as spectra go. Meaning it's a sum of it's a sum of shifts of the Eilenberg-MacLean spectrum, which gives the usual cohomology mod 2. Okay, so that's the plan for today. It's over to you, Philip.
Thank you. So, let's start with the universal R-plane bundle over the classifying space of R-plane bundle.
You need to ask questions. There isn't anyone else to ask questions, so it's going to be up to you.
Okay.
Okay. So, and then the MOR is defined, or TBOR, I'll also use this notation, is defined as the Tom space of gamma R, which is we take the unit disk bundle and we collapse the sphere bundle. So this is a spectrum because, well, it has suspension maps, which are given by the addition of a trivial line bundle. So in general, if we have sigma MOK, this is the same thing as a suspension of the Tom space of gamma R, gamma K, and suspension of Tom spaces is the same as the addition of a trivial line bundle. And then this gives us a map into, which is MOK plus 1. And then MO is MOK, TBOK, K greater than 0. Okay, now, so let's start first by computing the cohomology of the sort of pieces of the spectrum. So what is this mod 2? Or the reduced cohomology of this mod 2? So there is a lemma that we will use that says that if you have psi over a base B as an R-plane bundle, then you can have an isomorphism between the cohomology of the Tom space of psi and the cohomology of the base, this time not reduced. Okay, so Well, how to show this? So let's embed B as T0.
We saw this. We saw this in class.
Oh, okay. Okay.
Chipping.
So I won't.
Do you want? Do you want to see the proof again?
Yeah.
Okay. Well,
Okay.
in that case, let's go through the proof again.
Okay, sure. So let's embed B as the zero cross section in the Tom space. And then we can let T0 be the complement of this. In other words, we take d psi and we remove B. So this is contractible to the base point T0. And therefore, when we take the long exact sequence, T psi, T0, T0, with the mod 2 coefficients, we get that, so this will look like psi T0, T psi, yeah, T0, T0, T0. So because T0 is homotopy equivalent to T0, all of these will be 0. And so we get isomorphisms. So we have hi t psi T0 is the same as hi t psi T0. And then this by excision, so t psi T0 can be viewed as a subspace of E0, where here we remove the zero section. So this is the excision axiom on the cohomology. We get that these are equal. And then we have the Tom isomorphism from here to, well, the arrow goes the other way. I drew the inverse, but I'll just draw this. And this is the base, and this is all over the two. So basically, it's a sequence of isomorphisms. The first one comes from a long exact sequence. The second one comes from excision, and the third one comes from Tom isomorphism. And so in particular, we get Hn plus R T B O R reduced mod 2 is equal to Hn B O R mod 2. Now, since TBOR is a connected spectrum, or MO is a connected spectrum, so we can compute its cohomology groups as a direct limit, or sorry, inverse limit. So this
Perhaps it's worthwhile to say with respect to which maps.
Yes. So each so my understanding was that we have TBOR included in TBOR plus one, and so then this induces maps. In the other direction.
Well, we need to use the structure maps of the spectrum in some way. Otherwise, it's we get something which doesn't really tell us.
So this. So
yes, we have. Blah blah blah. Yes, we have these maps, and therefore there's a shift in there's a degree shift in the bottom arrow.
Yes, -1, right? Suspension increases by 1.
Is it -1 or +1?
Well, we increase dimension when we suspend, right? So then in the other direction, we start from a lower dimension and go to a higher one.
I think it's a +1.
Okay.
On the right. Yes, so we basically take the inverse limit, and this inverse limit is not as scary as it could have been, because everything stabilizes. So
yeah.
Is there a way to see this?
Yes, so that was exactly. So let's so we have HI. So we know that the cohomology ring of BO is just generated by the Stiefel-Whitney classes. So in particular,
BO is generated by the Stiefel-Whitney classes from the first up to the rth one.
Yes, exactly. Yeah. So I'll write it on the side here, just so we have it. BOR is equal to Z2. So in particular, if we take two distinct RNSs, where an I minimum of RNS, these will be identical. And then we apply the lemma to relate this to TBOR. We get this so we see that the groups stabilize. We can just choose for very large RNS. These are very these groups will be the same. So then this limit is just yeah. Okay. So then the next step is to show that actually we have more structure. It's actually it's this the cohomology ring has the structure of a free module over the Steenrod algebra. So should I recall what the Steenrod algebra is?
Well, just the definition and the properties that we
Sorry,
will
sure.
use.
So it's a graded, connected, non-commutative to Z2 algebra generated by SQI, which are maps on the Z2 cohomology with an increase in degree I. Sorry, that's not very clear. With SQ0 being 1, and then SQA, SQB being this. So these are called the Adam relations.
Okay, what does the product mean? Is it the composition, or is it something else?
So
SQA, SQB. Does this mean we apply SQB first and then SQA, and then we get what's on the right?
Yes.
Okay, so yeah, so we can compose operations, and this is what the product means on the left in this formula.
Yeah, and it's also got a co-product given by the Cartan formula. So SQK gets mapped to SQI, compose SQJ for I plus J is equal to K. So here it's multiplication. And so this is a tensor product.
Okay, and what is the letter on the left?
Psi is just the map co-multiplication map. So it's from A2 to A2 tensor A2.
Okay, so we have not only a product but also a co-product.
Co-product, yeah. So it's a Hopf algebra.
Well, it doesn't quite follow that it's a Hopf algebra,
but yeah.
Let's assume it is.
Okay, yeah. Okay, and so then we will need to use a lemma that basically says that if A, maybe I'll just say, so yeah, so we need to use a lemma. So if A is a connected Hopf algebra over some field K, and M is a connected co-algebra over K, that is also a left A module, and so maybe I'll write these as bullet points, will be clearer. So 1, 2. So M is a connected co-algebra over K, such that it's a left A module, and its co-product is a map of A modules. Then if the map V which takes an element A and multiplies it by 1, where 1 is the image of K, of the unit in K, in M0. So if this map is injective, then M is a free A module.
Okay, let's see if we understand this. Chipping, do you understand what's written?
So could you remind the Q algebra?
So connected, maybe I should define, I don't know, do you know what connected means? Should I define that? And
yes.
So connected means this. There's a co-unit map which goes from M0 to the field K, and this has to be an isomorphism. So that's what connected means. Yeah. And a Hopf algebra is a graded K module. That's an algebra, a co-algebra. It has a co-product, and the co-product is a homomorphism of graded K modules.
Okay.
Okay. This is just yeah. So we'll see these properties as we start to prove them for TBO, for the cohomology of TBO.
Let's come back to property 3. Chipping, do you understand what it says?
Proper 3?
The co-product.
No, the last one. It's not 3.
So this one. 2II.
The one.
This.
The one at the bottom. If mu or v egg is objective, then M is free. So A, what is A?
So A is an element of the A2 algebra. So V is a map from A to M.
Okay. From A to F. So on the left we have the action of no, sorry, on the right we have the action of A on F.
Yeah.
And 1 inside K is the same as 1 in M0 because we assume it's the same as K.
Yeah.
Okay.
So for our case, this map view will look like, so we have a map from A2 to the cohomology of TBO, and this is given by evaluating on the Tom class. So we had so to understand, so why does one go to U? Well, let's draw this commutative square. N plus K B O R. So this is SQK. Then here we have Tom isomorphism. And then so this square is not commutative. but if we modify it so that we multiply by the total Stiefel-Whitney class, then it will be commutative.
Okay. Let's see. So we have the
so SQ acts on U by omega E cup U.
What is
so
what is the okay? So the bottom arrow is what?
This is also SQ.
Okay, so the bottom arrow is the well, let's get rid of the M's and the K's and the R.
Okay.
So we have yes. So then the formula is correct. So we have SQ, which is a map from the completed cohomology, meaning the direct product of all cohomology groups.
Yeah.
And this is what we have in the bottom arrow, and on top we have the same thing, except we multiply everything by the total Stiefel-Whitney class, and
yeah.
And then we basically have the well, something we saw in class.
Yeah, and under this map we see that 1 goes to U.
Yes, and the modified diagram commutes. The SQ of U is the same thing as what we have in the bottom right place. Yes. Jiping, does any of it make sense?
Yeah, it makes sense.
Okay, cool. So well, okay, so the first thing is like a general fact is A2 is a connected Hopf algebra over Z2. So that's the first condition satisfied. Then the second condition, so how's the coalgebra structure given? Well, so we have the Whitney sum of vector bundles, which induces a map between the smash of the Tom spaces. And this induces the coproduct.
So the coproduct is a map from the cohomology of TBO to the smash of to the cohomology of the smash. Now the cohomology of the smash is a subspace vector subspace of the tensor product of the cohomology of why? Well, because because of what we saw in class. So the smashers, the Cartesian product with the bouquet collapsed, and it's it's an exercise, not a very difficult one to see that the cohomology of the smash embeds into the cohomology of the Cartesian product, which by the Gorinov formula is the same as the tensor product of the cohomology of the individual things.
Yeah.
Okay. So we have so this is the co-product, but psi or psi is not quite the co-product. Is the if we look at the formula where we in the lemma psi no I'm sorry, I think it's further up. There is a psi somewhere.
Here, another psi, like on SQ.
Yes. So this,
so maybe I should call it something different then.
This psi is not the same as the. Oh, sorry. No, this one is the same. Okay. So this is the code product. Okay. Okay. So we have a product and a co-product.
Yeah.
So we have a bi-algebra. A Hopf algebra to get a Hopf algebra, we need one more ingredient. We need the antipode map.
We need the what?
The antipode map.
But so the lemma only needs like A to be a connected Hopf algebra, not M. So
okay.
in this,
okay, yes. So this hold on. Then this the psi is is what? Which ingredient is so psi is in above psi was the co-product. Here psi is
it's the co-product for M. So maybe I should just distinguish
sorry,
them. So
yes, so there are two co-products. There's one for M and one for A.
Yeah. So this is psi A, and then this would be psi psi B.
Okay, well, maybe it's better to write psi M.
Sure. Sure.
Okay, so we have a co-product for M, which makes it into a co-algebra, and this is all we need.
Well, yeah, we also then need that it's a left A module and it's a co-product is a map of A modules. So it's a left A module by the action of the Steenrod squares, and it's
Chipping, does this make sense?
So here is one of the actions. You take SQ and you evaluate it on the cohomology class using the formulas that were defined previously. And then since suspension yeah, so sorry, and then you need to show that it's so then psi M is also a map of A2 modules, and to do this, you need to show that psi M SQK of X, well, this is just by the Cartan formula. To where psi of X is defined as this.
And what is x1 and x2?
So I said psi of x is defined as the sum of x1 and x2s. I'll put x, it's bad. I, j. So first we look where psi x maps, and then we apply SQ, and we get what's on the right hand side. And if we start with SQ of k, and we apply psi m, then using the Cartan formula, we get what's on the right hand side. So it is indeed a map of A2 modules. And the last thing we need to do to use the lemma is to show that it's injective. So okay. So proposition. The map to given by A to A. Okay. Well, so A2 splits as a direct sum of graded pieces of dimension k. So it suffices to show that for all kn is injective. So here I use the definition of the cohomology ring as the direct limit. And since these are stables, I just replace the star by r plus n, and just the whole spectrum by a piece. Okay, so let's to do this, let's start with psi, and this will be the trivial the line bundle times the universal line bundle times by itself r times. This is a bundle over BO1 to the power of r, and this in turn has a map to it's an r-plane bundle, so it's got a map to the classifying space BOR. So by naturality of A, we get A U psi, where U psi is the Tom class of psi, equal to, let's call this map G, the pullback GA of U. Now, if A of U is equal to 0, then this guy is also equal to 0. So actually, it suffices to show that evaluation from evaluation to the Tom space of psi is injective.
I'm sorry. What's the index on the right? Is it r plus n?
R plus n.
Okay. And what? So r is supposed to be greater
The rank.
than n.
Yes, r is greater than n here.
So
because to use this definition.
Okay.
Well, U psi is the product of Tom classes T gamma 1. And SQ of I of x1 xr is a sum of, can be written as a sum so y. So I'll explain the terms in the so here we take I is some index IR such that I alpha is greater than 2I alpha plus 1. So this is the basis in the Steenrod algebra.
What sort of basis? So first of all, SQ to the capital I is just the product of the SQ small i's.
Yeah.
So let's write this down. Okay. So there's there's a result by I don't know who that these SQIs with capital I being admissible, meaning what it says at the bottom is a Z2 basis of the Synod algebra. Well,
yeah.
it follows from the Adam relations, and let's assume it.
Yeah. And on the left-hand side, what is written is these VJs are determined by alpha appearing exactly I alpha minus 2 I alpha plus 1 times in each of these indices. In other words, J Vj equals to alpha is equal to I alpha minus 2 I alpha plus 1.
What is Vj?
So VJs are the power. So SQ, so the claim is this: SQI of this product of xi's is a sum of xi to the power of 2's. And this is proven by induction. I can go through it if it's necessary.
Well, maybe later.
Okay. Okay, so in other words, if we have some so the numbers vi determine exactly the image of this product of xi's. So if we chose I prime not equal to I, the indices vi would be different. Then
what are VI?
So actually, I did not understand this fully myself, to be honest. Like the definition that Weston gives is just this. So it's the like VI is it somehow counts the number of times that that we have I alpha minus 2 to the I plus 1.
The VI is a map from where to where? Okay, I'll have a look. So where is it?
So I believe it's in the proof, just under same page as definition 13, and then at the bottom of the page.
Which page is it?
Oh, I don't know the page, but section 12, definition 13, and then bottom of the page of that page, if that helps.
Well, firstly, there's a typo. It should be I alpha minus 2 I alpha plus 1, otherwise it doesn't make any sense.
Yeah.
And the VIs are the exponents of the 2's, which are themselves the exponents of the x1, etc., xr. Okay, well, basically it says that for each alpha there are this many so there are this many occurrences of alpha among the sequence v1 etc. vr.
Yeah, that's what I wrote in brackets. No.
Okay, so once to answer my question now I understand the answer to my question. The VIs are the expen so the VIs are defined in the third line from the bottom. These are the exponents of the 2's in the right hand side of the form.
Yeah.
Jiping, does any of this make any sense?
So VI is not a map, just an index.
Jiping, if it doesn't make sense, then please ask Philip.
So here your VI is not a map, just described as before. Yes.
Sorry.
So here you write VI is not a map. Yes.
Yeah, it's not a map that just counts.
Okay.
Yeah.
It's
so
the exponent.
yeah.
It's the exponent
of this. Yeah.
In this formula.
Okay.
Yeah, and different i's give different v's. So if initially we had something that was non-zero, then it's also mapped to something that's non-zero. So then our map was injective. So then v is injective, and then by the previous argument, the initial map is also injective.
Okay.
Okay. So then, okay, nice. So, well, corollary. is
just one thing. I've checked in Weston's paper. It's not V. It's new. It's a
sorry.
Greek. It's a Greek letter which is deceptive. It looks like V, but it's pronounced
Okay.
N.
Okay, new.
So
Well, yeah, backslash new, I suppose.
yes.
Right. So then we can apply the algebraic lemma, and we get that HTBO Z2 reduced is a free left A2 module. Okay. So then this is where we start relating it to the Eilenberg-MacLane spectra. So this is the same as, well, no, sorry. So let's look at the pieces. We have HNTBO Z2 is the same as HNTBOR Z2 for R greater than N. Okay. So in other words, HITBOR, I'm going to drop the Z2 coefficients, is a free left A2 module for I less than 2R and R. Now we can, for I less than R, HITBOR is just 0. We don't have any classes. And
sorry, before I forget, lemma, the word lemma is spelled with two M, and corollary
is with one R.
Is with one R, yes.
I was writing, a bit quickly, for sure.
Well, it's not very with two L's but one R. Well, technically there are two R's, but far apart. Anyhow.
Sorry.
No worries.
Right. So below R, it's 0. So actually, we have that H is a free left A2 module. Okay, so let's pick a basis. X1, XM. So each xi lives in H and I. So this corresponds to a map phi I into the Eilenberg-MacLane spectrum, shifted to the right by Ni.
Well, it's Z by 2 on the right.
Yes, yeah. And then we can sum all of these maps together. We get a sum of Eilenberg-MacLane spectrum. And so let's call this K. Let K be and so then we have phi, which is also the product. To K.
Okay, so we choose a basis for well, we basically have infinitely many generators of this free module, and we choose those generators which live in
dimensions less than 2 to the R.
Yes, which are from R to 2R.
Yeah.
Well, there are finitely many of those, and then we we take this K, and everything depends on R. If we increase R, we will get more summons in this sum. And so our goal, well, one of the goals for today is that when we take the whole sum, meaning just the tariff limit of the case for all R's, then we get the Thom spectrum, ML. Philip, does what I've just said make any sense?
Yeah. Well, yeah. This guy changes as R changes.
Yes, and if we take the direct limit, then we get everything.
Yeah. Yeah. So yeah. So this phi induces a map from the cohomology of K to the cohomology of TBOR. And so this map is we evaluate the basis on the Steenrod algebra. So
this time we consider TBR, which is a space. So
yeah.
So we also consider K as a space, which will be just the product of the Eilenberg-MacLane spaces K z by 2, comma, and I for finitely many i's.
Yeah.
Well, so we juggle between spectra and spaces, and we just hope that this won't lead us astray.
Right. So and this map is an isomorphism. In Z2, we have a basis here. It's QUI, where UI is
an isomorphism up from degree such and such up
in
to degree
Z2,
such and such.
Yeah, for J less or equal to 2R.
Well, basically, the cohomology of the Eilenberg-MacLane spectrum is the C-node algebra. So
yeah, yeah. So that's what I used here. So this is
yes, and the cohomology of the Eilenberg-MacLane space is the C-node algebra up to some degree.
J minus Ni and direct sum. So then we can pick a basis here in terms of the admissible sequences, and then phi and binaturality is this, and this is just by definition where UI is the generator. UI is the generator in this. And I, K, Z2, and I. So a basis maps to basis, and this is an isomorphism. So now we would like to. So we're going to try to use.
Let's recapitulate. We just showed that TBOR has the same cohomology. The space TBOR.
Yeah, the space
has the same cohomology as a product of the Eilenberg-MacLane spaces in degrees, basically up to R.
Yeah.
And this is all we know so far.
Yeah, this is all we know so far. So then I'd like to, for TBOR as a space, extend it to Z homology.
So we want, for some reason, we will see what the reason is shortly. We want to show that this map phi also induces an isomorphism of the integral homology or cohomology, which is basically the same in the same range.
Yeah. So we like later we want to extend this to a homotopy equivalence within this range, and to do that we need a Hurwitz theorem, so which requires isomorphism in Z homology. So before we extend to Z homology, let's look at exact. So to extend to Z homology, we'll use first some facts about the ZP cohomology. So I'll just rewrite. So if E is the total space, again, for gamma R, E0 is the complement of BOR. Then we have an exact sequence by looking at the pair E0 in ZP cohomology. So this we've already seen that it's the same as TBOR modulo a point. And then this is the same as BOR. And we also have a map So maybe we don't have these maps yet.
There's a problem there. Well, to use the Tom isomorphism, we need the bundle to be orientable with respect to this and with respect to z by p.
But this isn't Tom isomorphism. Which one? Which the first arrow is just excision.
Yes.
The first arrow is excision.
Okay, so this one works. Yes.
Yeah. Yeah. And then this is BOR minus 1 ZP. Basically, like what this map is well, sorry. I don't know what happened. So what this map is well, we take a plane, an R plane P, and a vector V in the complement of sorry, we take a plane and a vector that is in this plane. This plane is a plane given to us by like an R plane through the origin. We take an R plane through the origin. We take a vector, and then this map gives us the orthogonal complement of V in R. So this is a map from E0 to BOR minus 1.
Okay, so basically we have a homotype equivalence on the level of spaces.
Yeah.
So the space C0 is homotype equivalent to the space BOR minus 1.
Yeah. And so that therefore the cohomology groups are identical. So and it's known that for R very large, these are the same.
Well, for R very large with respect to
with respect to I, yeah. So for R very large with respect to I, these are the same. So then HITBOR mod T0 ZP is 0 by exactness. Okay. So then we can use universal coefficient theorem with field coefficients. By the way, so P is a prime odd. It's an odd prime. And so universal coefficient theorem, we have X to term 0. So then HTBO R T0 ZP is also 0. And very like in the same way, HI K ZP is 0. Well,
hold on. So this is again for I less than
I less than 2R.
Okay. So well, the second the last equality is basically true for all I greater than 0, and the first equality uses this restriction on I.
Yeah.
Well, in general, cohomology of or homology of K is two torsion and
tensoring by ZP is it gives zero.
We don't have any free components or other torsion. On the other hand, the BOR has it has two torsion, but it also has a free has the free part, and that's why the restriction. Hello. There.
So should I continue or should?
Yes, please.
Okay, so now we can. So now we have isomorphism in Z homology. So isomorphism in ZP for all P implies isomorphism in Z.
Well, no, not necessarily. We also need to consider the free part, which it could happen that all ZP cohomology are isomorphic, but for the wrong reason. So the let's see. So if we have a map of spaces which induces an isomorphism of all
on ZP for all P.
Cohomology with ZP coefficients up to degree something, then we basically what could happen, but I don't know if it does happen, is that okay, let's simplify. Suppose we have a map of finitely generated chain complexes or co-chain complexes over Z, and when we tensify ZP, we get quasi-isomorphism is the map itself, but quasi-isomorphism. Let's think. So in other words, if suppose we have a chain complex such that the homology vanishes in all when we tensify ZP. Does this mean that the homology vanishes itself?
But
well, and the answer is the answer is yes. Just by stupid direct calculation. Okay. So yes, it suffices to consider all finite field coefficients. Actually, all ZP coefficients. Philip, does this make sense?
Yeah, I think so. So here, what's important is that for each p we have 0. And if we had something else and they were isomorphic, then maybe it's not true.
Jipping, does this make sense?
Yeah.
Okay. We need to have a break soon. So, Philip, when would be a logical time to have a break?
I think now it's fine as well. Like, yeah. So
Okay,
yeah, we have
in this
isomorphism
case,
in Z, and then
yes. So let's have a
and then
20-minute break, and then we'll continue.
Yeah, maybe I'll just say then we apply. So then we apply Hewitt's theorem. So which says that if we have isomorphism in Z homology, we get isomorphism in homotopy groups for this range.
Okay, so in the Hoover's theorem for spaces, it's important that everything should be simply connected. Otherwise, it's more complicated. But let's look at the spaces K and TBL well, they're all simply connected.
Yeah. So we have pi I K equaling to pi I TBO R for I less than 2R.
Okay, and obviously the only interesting range is from R to 2R, but
yeah,
because the lower groups are 0. But anyway.
Yeah, I think I'm happy. Yeah, we can stop here.
Okay,
I think the next thing is the count.
Let's okay. No, this is not it.
Okay. Okay, so so yeah, we concluded last like 20 minutes ago that we have isomorphism in the homotopy groups for a range between R and 2R where they're interesting, and below R where they're trivial. And well, the homotopy groups of K are known. It's just the number of times Ni is equal to K. So this is Z2 to the M n plus R, where the integer mk is a count of the number of Ni equal to K. So now what I'm going to show is that actually Mn plus R is only dependent on n. So how so computing n plus R. Well, we've seen that the cohomology of K is the same as the cohomology of K is the same as the sum of the Steenrod algebras. in respective degrees, which is, so we get sum of dim a n plus r minus ni 2 from I equals to 1 to n. So here we just use the fact that K is a product of Eilenberg-MacLane spaces, and for each of these, there's an isomorphism between the Steenrod algebra and the cohomology. So then, so the dimension of these pieces of the Steenrod algebra are given by the number of dyadic partitions. So this is basically when you count your basis for admissible sequences, what you're doing is you're counting the number of dyadic partitions. So maybe I'll just define what is a dyadic.
Dyadic partition?
Yeah, so exactly. So a dyadic partition is a sequence of numbers such that it is a partition of n. And
well, it's not quite a sequence. It's an unordered sequence.
Yes,
meaning 3 plus 2 and 2 plus 3 are the same partitions of 5.
Yeah. So maybe it's better to define them as a set.
Well, it's not quite a set because 2 plus 2 is a partition of 4, although as a set it has 2.
Multi-set, I suppose.
So it's yes, it's basically it's an element of the symmetric power of the natural numbers.
Yeah. And so a partition is called dyadic if each of the I alpha has this form, 2 to the S alpha minus 1. And it's non-dyadic if for all alpha we don't have this.
Okay, so it implies in particular that most partitions are neither dyadic nor non-dyadic.
Yes.
Which is not very convenient, but anyway, this seems to be the terminology.
Yeah, but nonetheless, they have some nice properties, and they're directly related to the partitions that index the Steenrod basis, because sort of this dyadic partition is precisely the condition I alpha is greater or equal to 2 I alpha plus 1 minus 1. Right, so and then I'll rewrite this in terms of mk. So if we so this was a sum from I is equal to 1 to m. Now ni can take the values from n to n plus r, to r to n plus r. So if mk is the count of the number of times that ni is equal to k, then what's in this sum, we can just rewrite it as pd n plus r minus k, but then we need to multiply by the number of times that ni is equal to k, which is mk. And this time we sum from k is equal to r all the way up to n plus r.
Jipping, what do you think about this formula?
Maybe this is just a direct computation.
Yes, it is. But do you understand how to check this calculation?
Well, so look, here we have ni can take, so ni is either r, r plus 1, etc. To n plus r. So if we set now what I just gonna rewrite the sum, like nothing inside PD changes. I'm just looking at when ni is equal to k. And it's equal to k precisely mk times, which is mk was the number of times ni is equal to k by definition. So we need to multiply PD like partitions of n plus r minus k by mk. And we do this for all k between r and n plus r. Is it clearer?
Jipping?
Yeah.
Okay. Okay. So, and then there's a lemma. There's a lemma that says that if Pn is the number of partitions of n, a dyadic, non-dyadic, any partition, and we have this sum fn minus I times dyadic partitions of I, then f counts the number of non-dyadic partitions. So how to use this lemma? We want to relate this guy to partitions of n. Okay, well, what was this guy? This guy was the dimension of this space. But we know that the dimension, we know that we have isomorphisms between this, this, and this. We've shown all of these before. And so the dimension of this is known. And this has dimension partitions of n. So now we can apply the lemma. So this is the number of partitions of n. And then by the lemma, mk is just the non-dyadic partitions of n minus k. So mk is the non-dyadic partitions of n minus k. So in particular, mk plus r, yeah, was that yeah, no, mn plus r. We wanted to, mn plus r is just the non-dyadic partitions of n. And so indeed, it doesn't depend on r at all. So when we take the direct limit of these groups to get the sorry.
It's the direct limit, not the inverse limit.
Oh yeah, because we have homotopy groups. Yeah, it is. Yes. Then this is just the direct limit of zk's, z to the mn plus r, as we said, but this is just z pn d of.
Well, it's not z, it's z by 2.
Yeah. N. And this is so that's the result, I suppose. The homotopy groups of MO are Z2s.
That's the explicit answer. But to show that the MO spectrum is a direct sum of the Eilenbach planes, we don't need to know exactly the number of the summons. We have an isomorphism. We have a map K of R goes to
which we have TBO R. You mean goes to K? This map.
Yes.
Phi.
So there's a map like this. Then K depends on R.
Yeah.
And then we have this map on the level of spaces. Now, if we're able to check that we get a map from the spectrum TBO, which is basically MO.
So we need to check suspension, right?
To the direct limit of the KRs, then we're done, because basically the KRs passing from KR to KR plus 1 basically amounts to adding some new summons of which are all of the form H Z by 2 in some degree.
Yeah.
So which is basically straightforward from the way we construct K. What do we do? We take TBO, which we know to be the cohomology of the MO, and we added some new generators which occur in degree 2R plus 2, something like that, and 2R plus 1. And as for the previous generators, well, nothing changes. They remain the same. So we just add some new copies of blah 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 of H Z by 2, and we get a better approximation to MO. And the homotopy. So this argument shows that the homotopy groups of the spectrum on the right are the same as the homotopy groups of the spectrum on the left, up to some degree. But then, as we go to infinity, this becomes true for all degrees.
Yeah.
So we don't actually need the Horowitz theorem for spectra. We just use the fact that homotopy groups commute with colimits on
for spectra,
basically on the left and on the right.
Okay.
So we use the Hurwitz theorem, but for spaces only.
Mm-hmm. As yeah, as
Chipping, does any of this make any sense whatsoever?
Yeah, makes sense for me.
Sorry, I didn't catch it. Yes or no?
Yeah. Makes sense.
Okay.
So as an immediate corollary, you get a theorem of Rochlin, which basically says that any compact three manifolds bounds a four manifold. So to do this, we apply first Pontryagin Thom theorem. So and then so this is the limit. This is by MO. And so we need to count the non-dyadic partitions of three, and there are none. Like we can't split three into non-dyadic partitions.
Okay. Well, contrarily to what Weston says at this point, there is a direct proof which uses the Hegor decompositions, and there is a non no. This is the unoriented version. There is the oriented version as well, and there's also a direct proof.
And what's the direct proof for that?
Well, basically, we again use the Hegor decompositions, and then we do surgery on. We start with the sphere, which bounds the four disk, and then we do surgery to get a given oriented manifold, and we simultaneously do surgery on the bounding manifold. It's explained in the book by Praslov and Sosinski. I don't remember the name of the chapter, but it's there when they talk about surgery. So Praslov and Sosinski only talk about the oriented version, but there's a way to basically to do the same in the unoriented case as well.
Okay. Then the last thing is Stiefel-Whitney classes determine cobordism.
Yes, well, more precisely, the Stiefel-Whitney numbers.
Yeah. So this makes sense now, actually, because then basically then my argument makes sense yesterday. But with the classes, you're right, they're different. But the product of the numbers. Anyways, I'll explain.
Okay. And before I forget, there's a similar theorem in the non-oriented case. Stiefel-Whitney numbers and the Pontryagin numbers determine the oriented Fortism. But it's sort of more difficult to prove.
Okay. So.
And well, basically, we don't need two manifolds because Fortism are a group. It suffices to prove that if all Stiefel-Whitney numbers vanish, then the manifold is abounding.
Yeah. So this is let's take a class here. Let's look at its image under the Pontryagin Thom isomorphism, and then compose it.
Probably worthwhile to recall how exactly the isomorphism works.
Sure. So you take M, you embed it in some R n plus K, and then you choose a tubular neighborhood of M, and then you take its Thom space, which is you collapse everything outside Thom space of Vm, and this gives you a map from Sn plus K to TBOR.
Okay, so we have two maps. We have a map from M to BOR, and we have a map from the sphere to TBOR.
Yeah.
And these the second one is the Thom space construction applied to the first one. So we have an M which sits in R n plus K. Well, let's take the normal bundle. The normal bundle maps to well, in this case, it's TBOK.
Yeah.
So the normal bundle maps to BOK. So the manifold maps to BOK.
Yeah, and then you take the Thom space.
And then the Thom space maps to the Thom space, and we have a map from the sphere, the collapsing map from the sphere to the Thom space. So we compose. We go from the sphere to the Thom space, and then to the Thom space of TBOK.
Yeah.
Very well. And this is the Pontryagin Thom map, and we know that the manifold M is a boundary if and only if the resulting map from the sphere to TBOK is zero when we take the limit. It may not be zero on the nose, but it needs to vanish in the limit.
Yeah, and so then I will use the fact that we've already shown that these are isomorphic. So we have an injection in particular into the homology of TBOR, and I will denote this composition by theta. And then I will need something else. So then I will look at the Thom isomorphism.
And by the way, there's a simplification since we know that the sequence of the homotopy groups stabilized. We can take K so large that the class will the class of the map from the sphere to TBK will actually be zero. So we don't worry. We don't need to worry about passing to the limit afterwards.
Yeah, you're saying you can replace this by just some very large n.
Yes. So
and then this is just isomorphism of groups.
We need to okay. So we need to say
so for a fixed m, we can choose n very large.
For a fixed n, we can choose r large enough.
Yeah.
So we fix an n and then we vary r.
Yeah. So n plus r.
And then capital R on the right as well.
Yeah. So the Thom isomorphism goes from BOR to Hn plus R E mod E0, which is the same as the reduced of this.
This time is the same R, both on the left and on the right.
Yeah. Yeah. So what it does is it maps a Stiefel-Whitney class to the push forward of the projection, cup the Thom class. So we have the projection from E to BOR. This induces a map pi star. And then we also have
what is pi lower star of the projection?
So we
isn't it supposed to be pi upper star?
Yes, sorry. Yeah.
So here pi is the projection from is the projection of the universal bundle.
Yeah. And U lives in HR E 0. So and I will denote this omega I squiggle. And then I'll consider the product omega I with theta m. So this we have a homology class of dimension n plus r, and we evaluate it on a Stiefel on a cohomology class of dimension the same.
Mm-hmm. And what is theta?
So theta m is the image of m under this map.
Okay.
Okay, and then we use the formula that we deduced. So pi omega I cup U theta m. And this is so a cup product sort of it commutes with the cap product in this way, theta m cap U.
Well, then it's just W on the left.
Yeah, that was the next step. So okay, well, I'll just do it from here. So and then this is just M. So in particular, if M is, if all the Stiefel-Whitney classes are 0, then M is 0. So we can take theta M minus theta N.
And also, you need to replace a small I with capital I in all
Yes.
formulas, starting
Yes.
from the second one.
Yes.
Chipping, do you follow?
Yeah.
So then let's be careful here. At the moment, we just have Stiefel-Whitney numbers of the normal bundle. So omega I here are to do with the normal bundle. So how to translate them to the so I'll remove this. I'll write this later. And so omega I v mu m omega I Tm are equal to 1 because the normal bundle and the tangent bundle are trivial.
Well, this time it's not Wi. It's just W.
Yeah. You're right. Total. The total.
Stiefel-Whitney classes. Yes.
Yeah. So then, I mean, here we can pass the total as well. So this holds for all I.
Well, yes, but this is not the same as the total Stiefel-Whitney class evaluated at integrated over M, because there will be just the contribution from the top class, and everything else will be 0. So here, I think Weston does something strange, and I'm not sure. I'm not sure it works. What is true is that if all tangent Stiefel-Whitney classes are Stiefel-Whitney numbers are 0, and so are all normal Stiefel-Whitney numbers, and vice versa. So there's a lemma. There is a lemma in Weston's notes. Let me find it. So the lemma. I'm sorry. I'll find it. A minute. Okay. So the So the correct lemma is proposition 9.3.
Okay.
So proposition 9.3.
So sorry, which book?
Yeah, so maybe we should have started with it, but let's write it down at this point. So the talk follows notes by
Introduction to Cobordisms, right?
Western. I don't know the first name. Introduction to Cobordism, which can be found online by googling.
Okay.
Okay, so lemma. Sorry, proposition 9.3 is correct, but then at some point Weston says that the tangent Stiefel-Whitney numbers are equal the normal Stiefel-Whitney numbers, and basically this is strange.
Yeah. But we don't need this, right? Because then we say
we don't need this because we were able to say that if all tangent Stiefel-Whitney numbers are 0, then all normal Stiefel-Whitney numbers are 0, and vice versa.
Yeah. So this is an if and only if, and that gives us what we wanted, which is that for the Stiefel-Whitney numbers of the tangent bundle do indeed determine cobordisms.
Okay, and so more precisely, if we replace m with n
minus n, yeah,
disjoint n, we get we get a corollary the m disjoint n is coordinate to 0, meaning m and n are coordinate if and only if all Stiefel-Whitney numbers go inside. Okay. Well, is there anything else you planned to talk about?
No, that was it. I was gonna say you can actually pick generators for these guys for the Z2s and their where is it? Yeah, so there's actually explicit generators we can choose here, which are either RP or some hyperplanes. But I haven't prepared fully to do that. But so
okay,
just maybe mention it.
So in fact, the ring. So the cobordism ring is a ring, and we have computed the group structure, but it's also possible to compute the ring structure. And it turns out that the ring is a polynomial ring with one generator in each degree, 2 to the something minus 1.
Not 2 to the something minus 1.
Oh,
non that.
The opposite.
Yeah.
And those generators can be chosen explicitly to be either the projective spaces or hypersurfaces in the products of projective spaces. Well, this is a direct check. Now, the only thing that's not clear at the moment is that these generators free to generate everything. Is there a way to prove this? not too expensively.
I mean, he sort of says something. He like writes matrices and then well, he doesn't write matrices. He says you should write down matrices and these like split and these split over the basis, so it actually generates everything, something like that. But I haven't yet. I didn't have time to fully understand it.
Well, it's basically a calculation. We take those generators and then we calculate the Stiefel-Whitney numbers of all possible products, and it turns out that those are indeed generators. So it's well, it's not a philosophical proof, but it's a proof. Okay. Are there any more questions or additions? Please save the notes.
Yeah, of course. They're not Zoom notes, so they'll have like they're just already saved.
Okay, so once you have them, please send them to me. I'll post them on
the drive
on the web page. Okay. Well, this is it. The seminar is over. Is there anything else we want to talk about today? Well, it looks like the answer is no. I'll turn off the recording.